Hello students. So till the previous lecture we have studied the rotational spectra of rigid diatomic molecule and non-rigid diatomic molecule. But in the today's lecture we are going to study it for the polyatomic molecule. So what happens for the polyatomic molecules? So I will take an example. OCS can be taken as example, or HCl, HC, triple bond, CCl. So what happens for this type of molecules? So we know that for diatomic molecule, we are taking for the non-rigid one. So epsilon j is equal to b j into j plus 1 minus d j square j plus 1 square plus dash dash centimeter inverse. So for this, the separation for the spectral line is 2b, which is further modified by the distortion constant. Okay, so we will consider this rotation spectra of polyatomic molecule by one. So the first point is that the moment of inertia of end over end rotation of polyatomic linear molecule is greater than the diatomic molecule. So see, for that first we are studying for the linear molecule. Okay, we will look only for the linear molecule. So here we have taken the example of linear molecule. So for the linear molecule we know that IB is equal to IC. Is it okay? And where IA is equal to 0. So here there are three moments of inertia in which the one is 0 and the other two are equal. Is it okay? So the moment of inertia here is only for end over the end rotation, whether it is in the plane or the perpendicular to plane, but the moment of inertia is considered only for end over end rotation. Is it clear? So the value obtained of moment of inertia for the polyatomic molecule is greater than that of diatomic molecule. So this is the first point. As the value of moment of inertia is greater for the polyatomic molecule, see, this is for the polyatomic, which is greater than the diatomic. But the value of B for polyatomic molecule is less than that of the value for the diatomic molecule. Is it okay? Is it clear? So here the B value observed for diatomic molecule is 10 centimeter inverse, and value of B for triatomic molecule is 1 centimeter inverse. Is it okay? For larger molecule it is still small. That is when we will move from the triatomic to pentaatomic or hexaatomic, that value will decrease steadily. Okay. The second point is that the molecule must have, that you know, that molecule must have the dipole moment. Then and that molecule will have the rotation spectra, or we can say it is said to be the microwave active. Okay. So OCS is microwave active, but carbon monoxide or carbon dioxide, it can be written as OCO, which is microwave inactive. So if we substitute the isotope of oxygen, that is O16, C and O18, then also it is microwave inactive. So you may say that if we are substituting it with the isotope, so it must be microwave active. But what happens? The isotopic substitution does not leads to change in dipole moment, or it does not introduce the dipole moment. And thus, because the bond length and the atomic charges are unaltered by the substitution, and therefore the carbon dioxide remains microwave inactive. Is it okay? The third point is that any polyatomic molecule having n number of atoms will have n-1 bonds. Yes or no? So if we take the example of again OCS, as there are 3 molecules, there are 2 bonds. That is, n atoms will have n-1 bond. Is it clear? So as there are n-1 bond, we have to determine the value of individual bonds from the spectrum. But as we know that from the spectrum we only get the one value of B. Is it okay? So consider the triatomic molecule OCS. So in this there are two internuclear distance, that is RCO and RCS. Is it okay? There is only one moment of inertia for the end over end rotation. Only one moment of inertia for end over end rotation. So see, I will draw one table. So observing this table, we come to know that the value of B is constant and it is 0.2027. So we know that B is equal to H upon 8 pi square IC. So now I is equal to H upon 8 pi square B into C. So when we calculate the value of I, and it comes to know that the value is 137.95 into 10 raised to minus 47 kilogram meter square. But from this value it is unable to deduce the value of RCO and RCS, isn't it? So from just one value of I, it is really impossible to deduce the value of two internuclear distances. So now what should be done to solve this problem? We should do the isotopic substitution. That is when we will replace it by its isotope, we will get the two values of I, that is I and I dash, and by comparing the value of I and I dash with the value of R, we will get the value of internuclear distance. So to find the internuclear distance, here we will consider an example. See, this is the atom of oxygen. This is for the carbon, and this is for the sulfur. So see student, these are the internuclear distances. So imagine that here is your center of gravity. So this distance is RC, this distance is RO, and this distance is RS. Okay, this distance is distance between the bond RCO and this between the RCS. Is it okay? So now you know the meaning of each term. Okay, so we know that at the point of center of gravity, this mass into radius is equal to this mass into radius. But here at this side there are two atoms, that is oxygen and carbon. So MO RO plus MC RC is equal to MS RS. Is it okay? We know that I is equal to summation of MI Ri square. So now I is equal to M0 R0 square plus MC RC square plus MS RS square. This we will denote it as a equation 1. Is it clear? Now we know that RO is equal to RCO plus RC and RS is equal to RCS minus RC. See, I will show you the diagram again. So, RO is equal to RCO plus RC, whereas RS is equal to RCS minus RC. That only we have written here. So now, we know that MORO plus MCRC is equal to MSRS. So M0 is equal to, substituting the value of R0, that is RCO plus RC plus MCRC as it is, MS substituting the value of RS, that is RCS minus RC. So now M0 RCO plus M0 RC plus MC RC is equal to MS RCS minus MS RC. So whatever the terms that are having RC, you will take it to one side, that is M0 RC plus MC RC. This minus will become plus MS RC is equal to MS RCS minus M0 RCO. When it will shift here, it will become minus. Now, taking RC common, what remains? M0 plus MC plus MS into RC is equal to MS RCS minus M0 RCO. So MO plus MC plus MS is equal to the capital M into RC is equal to MS RCS minus MO RCO. This is equation 2. Is it okay? Now, what you have to do, we know that I is equal to MORO square plus MCRC square plus MSRS square. Okay. Now, again, substituting the value of R0 and RS, that is R0 and RS in this equation number 1. So, M0, R0 is RCO plus RC square plus MC RC square plus MS, RS value is RCS minus RC square. Now solving this square bracket, see, RCO square plus 2RCO into RC plus RC square using the formula of A plus B bracket square plus MC RC square plus MS RCS square minus 2RCS into RC plus RC square. Okay, now solving this or solving the brackets, MO RCO square plus 2MO RCO RC plus MO RC square plus MC RC square plus MS RCS square minus 2MS RCS RC plus MS RC square. Okay. So now what we will do? We will take the terms having RC square common. It will have, this term will come common. So what is there? MO plus MS plus MC into bracket RC square. Okay. Now the next thing that we will take common is the factor having RC. So these are having the RC term. So RC and also 2 is common. So we will take this common. 2 RC MO RCO minus MS RCS. Whatever the remaining things are this. That is plus MO RCO square plus MS RCS square. Is it okay? Now this is capital M RC square plus, now pay attention here that we know that M, see this equation number 2, MRC is equal to MS RCS minus MO RCO. Here there is a MO RCO minus MS RCS. So writing here minus MRC. What will we remain? Plus MO RCO square plus MS RCS square. Is it okay? Now solving it, MRC square minus 2MRC square plus MO RCO square plus MS RCS square. So what will remain here? Minus MRC square plus MO RCO square plus MS RCS square. Is it clear? So therefore I is equal to MO RCO square plus MS RCS square minus, now substituting the value of RC square, that is M into, according to equation number 2, MS RCS minus MO RCO square upon M square. Okay. So now this one of the M gets cancelled. What remains is MO RCO square plus MS RCS square minus MS RCS minus MO RCO square upon M. Is it clear now? Is it clear to you? So see student, for such type of derivation, what you have to do, you have to watch this video and try to derive this equation in your notebook. Okay. The next point is, from this equation we can find out the value of moment of inertia, which depends on the two radius. But how to distribute between these two radius is that we have to do the isotopic substitution, that is I dash, where we are substituting the isotope of oxygen. So mass of oxygen will change, that is MO dash, and also RCO square plus MS RCS square minus ms RCS minus mo dash RCO bracket square upon m dash. So what will happen when you will substitute it? Some of the terms will get cancelled and you will be able to find the distance or the internuclear distance. Is it okay? So whatever the derivation we saw, that was for the linear molecule. The next is the symmetric top. So for the symmetric top, IB is equal to IC, but which is not equal to IA, and IA is also not equal to 0. Is it clear? So for the symmetric top, there are two moment of inertia. Yes or no? So it becomes more complicated, and we have to introduce the new quantum number, that is k, where k is equal to j minus 1, j minus 2 up to 0, again so on. So when we introduce the new quantum number, the expression for epsilon j changes. So epsilon j k is equal to bj into j plus 1 plus a minus b k square. Is it okay? So what does this a and b relates? So b is equal to h upon 8 pi square I b into c. So here there is a I b, and a is equal to h upon 8 pi square I a into c. So these are the two different rotational constants for two different moment of inertia. So the selection rule is delta j is equal to plus minus 1 and delta k is equal to 0. So student, as you have to appear for the MCQ type of exam, so these are the small points that you have to remember, okay? That the selection rule changes for each and every type of molecule, or for polyatomic molecule it is different, for diatomic molecule it is different. So now for the third, that is a spherical top molecule. So see, for the spherical top molecule, what happened, that it is microwave inactive. Okay. Now fourth is a asymmetric top. So for the asymmetric top molecule, it becomes more complicated, okay? It is more complicated to solve for three different moment of inertia. Is it okay? So it is more complicated to solve for the three different moment of inertia. Okay. So student, here our chapter first is finished. Okay. Thank you.